Welcome to Calculus. Today we will investigate an application of finding limits of average rates of change, focusing on finding velocity in a free fall scenario by applying this limit strategy to a given position function. Let's head over to our notes for a scenario. So here's the given scenario. We're given a position function, so S of t equals negative 16t squared plus 700, which gives the height in feet of an object that has fallen for t seconds from a height of 700 feet. The velocity at time t equals a seconds is given by the limit as t approaches a of the average rate of change S of a minus S of t over a minus t. So the specific scenario is that a tourist drops a burrito from a top floor of the Fountain Place Tower in Dallas, which is a height of 700 feet. The question we want to answer at first is how fast is the burrito falling at time equals 3 seconds? So we want to begin by just creating our average rate of change fraction. So we'll define some items here. We are looking for the limit as time approaches 3 seconds. And for our numerator, we want to fill in both the function itself and the function with this a value of 3 substituted in. So in fact, that's what we'll write first. That's our S of a. So what I'm going to do is I'm going to take this original position function, but anytime I see time, I'm going to substitute the specific number 3. So the way that looks for us is going to be negative 16 times 3 squared plus 700. And that's that S of a. I'm going to subtract from that the original function as it is. So S of t, the position function for this falling burrito. So that difference is going to be negative 16t squared plus 700. And then similarly for the denominator, I want to substitute in that time value specifically for a. So we're going to record down in the denominator 3 minus t. So there's our setup for that average rate of change for this position function. And at this point, what it represents is the velocity of the burrito 3 seconds into its free fall from the top of the Fountain Place Tower in Dallas. Our task at this moment is to simplify the fraction. And then once we've done that, take the limit. Well, let's work on the simplification first. So the first thing I want to do is really deal with this numerator. So I see that I've got negative 16 times 9 plus 700. And at that point, I can let that set of brackets go. I can also let the parentheses go on the second expression there by distributing this negative sign. So I see it's going to change the sign on both terms. So that's plus 16t squared minus 700. And then for that denominator, I do have in mind how I'm going to take this limit. I want to cancel the denominator, but I have a feeling that the t needs to go first. So instead of 3 minus t, I want to factor out a negative 1 and then switch the places so that this is now t minus 3. And I don't want to forget that I am taking the limit as time approaches 3 seconds. At this moment, I can cancel some terms up in the numerator. So I notice that I've got plus 700 and minus 700, and those will cancel out. So what I've got left at this point is simply the limit as time approaches 3 of, and then I'm going to switch these places, 16t squared minus, and then 16 times 9 is going to give us a larger number, but I'm going to leave it unfactored or undistributed. We'll see in a moment why that's an advantage. I'll record what I got in the denominator. Now, the reason that I leave that 16 times 9, I could have multiplied that through, and that would have given us, I believe, 144. But what I want to do instead is factor out a 16. So I'm going to wrap around to the next line and factor out 16. So the limit as time approaches 3. And what's left when I factor 16 out is t squared minus 9. Now I'm starting to recognize that as the difference of two squares. So I can factor that further in my numerator as, well, let me get there. The limit as t approaches 3 of 16. I can factor t squared minus 9 as t plus 3 times t minus 3. And that is going to be a great advantage because now I can cancel this binomial t minus 3 in the denominator. So I'll do that without any further hesitation. And we're getting close to being able to take the limit. In fact, I'm going to write the simplified limit expression. It's limit as t approaches 3 of 16 times t plus 3 over negative 1. And now because that denominator term t minus 3 that would have made this undefined is gone, I can use direct substitution. So now I'm going to let the limit part go, and I'm going to substitute 3 for t. So that's 16 times 3 plus 3 all over negative 1, which is going to be 16 times 6 over negative 1. And that reduces down to negative 96. And if I think about it in terms of the falling burrito, that's its velocity, feet per second. Why is that negative? Well, remember from physics that velocity is a vector. So it's got both a magnitude and a direction. And as it's falling towards the Earth, we would consider that that is the negative direction, whereas away from the Earth would be positive. Okay, so first question answered there. A nice application of taking the limit of an average rate of change to find the velocity if we've got the position function. Let's take a look at our next question. So the next question is simply, when will the burrito hit the ground? So what we've got to use here again is the position function. So I'm going to pull it again. It's s of t equals negative 16t squared plus 700. But I'm going to make a change because I need to think, what height above the ground is the ground? That height has got to be 0. So I'm going to replace the s of t, the y or the dependent part of that function with 0. And I'm going to set that equal to the right-hand side, negative 16t squared plus 700. And if I can solve that quadratic equation, then I should have the time it takes for the burrito to hit the ground. Many different ways to solve that. I'm going to solve it by taking the square root. Since I don't have a b term in this position function, so I'm going to subtract 700. And that'll give me, I'm going to move over here to the right. Negative 700 equals negative 16t squared. And then to isolate the t squared part of that term, I'm going to divide by negative 16, cancel that, divide also negative 700 by negative 16. And at that point, what I get, again, I'll keep moving to the right, is positive 175 over 4, if I reduce negative 700 over 16, equals simply t squared. And then to solve for just t, I'm going to take square root. And that is the expression. I'm going to leave that in. The time it takes for the burrito to hit the ground is the square root of 175 over 4 seconds. And I'm going to leave that as an exact answer. Now, we're going to need to use that for our next question. So the next question is similar to what we just looked at with the time approaching 3 seconds. But now the question is, at what velocity will the burrito hit the ground? So we've got to write the limit again, but we're going to use this expression for time, square root of 175 over 4, instead of 3. So let's rewrite that again. So we're going to use the limiting process of the position function. So again, I'll write the limit as time approaches, in this case, the square root of 175 over 4, since that's the amount of time it'll take for the burrito to hit the ground. And then again, I want to record this as the average rate of change fraction. So recall that was S of A minus S of T over A minus T. And we were saying that this, if I take the limit as T approaches A, that is velocity as a vector. So let's do that again, but now using this time to hit the ground. So we're going to just substitute as we did before. So it's the same position function, negative 16 times, in parentheses, now the square root of 175 over 4 squared plus 700 minus, and then this is the original function in parentheses, negative 16t squared plus 700 all over the square root of 175 over 4, so that time to hit the ground, minus t. All right, so there's our setup. And again, just like we did with our first limit of the average rate of change, I want to simplify that numerator first. And again, my goal ultimately is to cancel the denominator so that I can use direct substitution to find the limit. Well, let's simplify. So I'm going to actually leave this expression pretty much unchanged because I want to kind of keep 16 ready to factor out. So I'm going to call this negative 16, and I'm even going to leave the square root of 175 over 4 squared. I'm not going to cancel that because I remember from my previous question, the first question here, I ended up factoring a difference of 2 squares. So I want to keep that visible. But I do want to distribute this negative through the original function. So that becomes plus 16t squared minus 700. And then I remember what I did before is I factored out a negative 1 so that I could invert the places of the t and the square root of 175 over 4. Again, all these algebraic changes are with cancellation in mind. I'm going to wrap around here to the far left. So it's still the limit as time approaches square root of 175 over 4. And I do need to notice some cancellations in my numerators. The 700 constants cancel again. 700 minus 700 is 0. And then I'm going to rewrite that numerator as 16t squared minus 16 times the square root of 175 over 4 squared, all over, I'm going to leave this the same in that factored form, t minus square root 175 over 4. And now I'm ready to factor that 16 away. So that is the limit as time approaches the square root of 175 over 4. Factor the 16 out, and then what's left is t squared minus the square root of 175 over 4 squared. And at that point, I'm seeing again the difference of two squares pattern. So as I record this denominator, I'm preparing to cancel this t minus 175, I'm sorry, square root of 175 over 4. So our next step, we'll do that. Let's factor the difference of two squares from the numerator. So the way that'll look is as 16 times t plus the square root 175 over 4. And the other factor, t minus square root 175 over 4, all over negative 1 times that same factor. So I am ready to cancel. Let's do so. So these identical factors will go away. And at this point, because of that cancellation, I'm now free to use direct substitution to evaluate the limit. And that is going to bring us to this velocity when the burrito hits the ground. I reckon it's traveling pretty fast if it's fallen from the top of the Fountain Place Tower. So the expression left is 16 times parentheses t plus square root 175 over 4, all over negative 1. That's all that's left in denominator. So I'm going to substitute now, direct substitution. I'll drop the limit. So that's equal to 16. And I'll put, instead of time, this time value of square root 175 over 4. And that's duplicated. So I end up with 2 of these, all over negative 1. And that's going to reduce down to, I've got 2 of them. So if I treat that as a coefficient of 2 and multiply it times the 16 and then wrap the negative into that, we get negative 32 times the square root of 175 over 4. And let's get a decimal value for that, since we are interested. How fast is the burrito traveling? That's an exact answer, but let's type that in and get an approximate decimal. So we'll type this into Desmos. Negative 32 times the square root of the fraction 700. Wait, let's reduce that. We had 175 over 4. And that burrito is moving. So that's negative 211.7 roughly. And I believe that's feet per second. Let's head back and finalize that answer. So roughly negative 211.7. And let's just confirm our units. So I see that it's in feet. So that's going to be feet per second. Okay. So a nice application of taking the limit of an average rate of change to find velocity of an object in a free fall scenario where I know its position function. Thank you for joining for this example. I'm going to let you go work on your own examples of free fall situations now. Thanks for joining. See you soon.